Okay, our topic is 3.3 environmental impact on enzyme function. So, we've been talking a lot about enzymes, and now we're going to look at the environment around it and see the impact that it has. This is really the focus of your lab that you've been working on. So, we're going to first start by talking about the structure of an enzyme and how that affects its function. So, just a quick reminder, we remember that we have an enzyme and we have a substrate that needs to bind to that particular enzyme. But there are times where things in our body are going to make it so that these things are not able actually to bind. And so we know that this shape is really, really, really important. If that enzyme shape is altered, we know that there's going to be something that happens so that we are not able to take our substrate and then be able to have that reaction to occur. We want enzymes so reactions can happen quickly. And so when you look at this, we're going to talk about two things. One of them is going to be denaturization. And the other thing we're going to also talk about is going to be what that impact is going to have on the enzyme's function. So when we look at this, we know that enzymes, I'm going to move this, function normally is going to be a normal protein, but this normal protein in its tertiary structure again can actually be denatured. And when it is denatured, we will see that it no longer has this 3D shape of the normal protein, and instead it's going to look broken apart or denatured instead. And we know that when this happens, that enzyme is not going to be able to work the way that we want it to. So the ways that this can happen is one, that there's an environmental temperature change. You want to make sure you write that down. Number one is temperature change. Number two is that the environmental pH can lead to denaturization as well. So we will see that there's going to be a problem if that pH changes. So one is temperature, two is pH. And this process, when this happens, it is typically irreversible, which means when this happens, the temperature increases, that enzyme is done. It's not going to work. We can't fix it. And so it's lost or it's severely decreased in terms of its ability. But in some cases, it is reversible and it does allow that enzyme to regain its activity again. But again, like I said, in most cases, it's going to be that it's irreversible typically. So we're going to talk about how the environment impacts the activity, focusing on temperature and pH first. When we first focus on temperature and pH, we're going to see that these reaction rates are going to change. And so we know that those temperatures, when they increase, we're going to see that a different reaction rate is going to happen. So when we look at this here, we know that enzymes have an optimal temperature. Our body is a particular temperature for a reason. You are not 98.6 degrees just because your body wants to be. It is because it's optimal for humans to be that temperature for your enzymes to be able to speed up those biochemical reactions that we want to happen. So the range in which the enzyme mediated reactions occur the fastest is going to be optimal. And these reaction rates change when the optimal temperatures aren't maintained. So when your body is up to a really, really high temperature, these reaction rates cannot occur the way they're supposed to. When we change the temperature in our environment, it's going to initially increase the reaction rate. So it's going to increase the speed of those molecules moving. It's going to increase the frequency of the enzyme substrate collisions, which we want. But at a certain point, the temperature is going to increase outside of the optimal range. And in that case, the enzyme is going to denature. So as you see in this graph here, we can see temperatures increasing, the rate of reactions getting better, getting better. Oh, we're at optimal temperature. This is best for reactions to happen. Enzymes and substrates are binding at a great rate. And then all of a sudden, you see this decline in the rate of reactions because we're past that optimal temperature and no longer are we going to be able to have our enzymes and our substrates binding, and the enzymes in particular are going to denature. We're going to also see, though, on the other hand, that environmental decrease in temperature. So if the environment temperature goes down, it's going to also slow that reaction rate. We see that here, that this reaction rate is really slow with a low temperature. And so decreased frequency of the enzyme substrate collisions are going to happen. But it's a little different. It's really not going to disrupt the enzyme structure. And so it's not going to denature them. It's just going to slow the reaction rate. We're going to look at pH next. And with pH, I'm not expecting that you know how to use this equation because AP doesn't expect you to know this equation. But I do need you to understand that if we're on a 0 or 1 pH scale, we're talking about something very acidic. If we're 7 and 8, we're neutral. And if we're up to the 13th or 14th, we're talking more about a basic solution. And the equation is on your AP exam sheet. It says pH equals the negative log 10 of the concentration of hydrogen ions. So, what I need you to understand is this graph here. And that is that if we have a really low concentration of hydrogen ions, we have a very basic solution. But as the concentration of hydrogen ions increases, we're going to have a much more acidic environment that our species is going to be in. And that's going to then impact if our enzymes are going to be able to work or not. And this is going to be related to your lab. When you look at this here, we see that the pH is going to measure the concentration of hydrogen ions. And I just talked about that there. And it's a logarithmic scale, which means that if the pH of 6 is going to have 10 times more hydrogen ions in solution compared to a pH of 7. But just like temperature, there is an optimal pH range. And so the range that in which the enzymes reactions can occur the fastest is going to be in the optimal range. So changing the pH outside of this range is either going to slow it down or stop the enzyme activity completely. And enzyme denaturization can occur as a result of an increase or decrease in this case outside of optimum. So changes in that hydrogen ion concentration really is going to have a huge impact. And so we need it to be in the exact optimal pH in order for the enzymes to be the most efficient they possibly can be. We're going to see here that the substrate amounts also impacts it. So we've talked about the temperature, we've talked about the pH, but just having a lot of substrate is also going to be good. And this makes sense because the more substrates that we have, the more likely it is that they're going to collide with the particular enzyme. And substrates will eventually become saturated, which means that we'll see no more increase even if we keep adding more substrates to the reaction. So the reaction rate will actually become constant or maintained. And the reason this is if we increase the concentration of our products, we decrease the opportunity for the addition of substrates because matter does take up space. And so the more product means the lower chance that we're going to have an enzyme substrate collision. So, like we see here, our rate of reaction is going to increase the more substrate we have. The more substrate we have, the more likely it is to bind with that particular enzyme. But at a certain point, more substrate isn't going to do anything for us and we're not going to see that that reaction rate's actually going to increase. We're going to also see this with changes to enzyme concentration is going to slower the reaction rate. So if we see that we have less enzymes, so less enzymes, even there, we're going to have a slower reaction rate because no matter how much substrate you add to it, if we have less enzymes there, our reaction rate's going to slow. There's less opportunities for our substrate to actually collide with those active sites. But the more enzyme that we have, the faster the reaction rates are going to happen because there's more opportunity for substrates to collide with those active sites. And so you can see here that our substrate is going to be limited. But our enzyme concentration, as we increase in our enzyme concentration, that's going to be good. But again, substrate is limited at a certain point. So we're going to talk, the last thing is about competitive inhibitors and non-competitive inhibitors. And if this video is making it so that you need to take a break, you could pause the video now and then come back. But if you're feeling good to keep going, we're going to talk about the last two things. Competitive inhibitors are going to be something that's going to bind to our enzyme, and it could be reversible or irreversible in this case. So what's going to happen is it's going to compete with the normal substrate for that active site. So it's like a fight here. This one here, competitive inhibitor, can fit into this active site, but so can our substrate. And so whoever gets here first gets it. And so if our competitor inhibitor takes all the enzymes up, you know that your substrate no longer can bind to that particular enzyme and the reaction can't go faster. So if we see that there's more inhibitors than there is substrate, our reaction is going to slow. If our inhibitor concentrations are very low than our substrate, then it can happen normally because we know then that they're going to bind. It's a numbers game. If we've got lots of substrate, not many competitive inhibitors, our substrate's going to do just fine and it's going to get to those sites. But if every single time that competitor inhibitor jumps in there and takes that site and there's too many of them, then we know it's going to slow down. If the inhibitor is binding as irreversible, then that's fine. As that competitor inhibitor gets off that spot, then that enzyme can function again. But if that inhibitor binds and it's irreversible and it can no longer detach and it's stuck here forever, then that enzyme is useless to us and we can't use it. So these are competitive inhibitors. They're like the competitor little people running around trying to steal that chair. And I always think of it like when you play the game where there's chairs, like musical chairs, and it's whoever's going to jump on that spot and take that spot first, they're going to be the competitive inhibitor. But that substrate really wants that spot. Non-competitive inhibitors are a little different. So enzymes have a region other than the active site that something can bind to, and we call this the allosteric site. So this allosteric site is going to not be the active site, but a different site here. And these non-competitive inhibitors aren't fighting for the active site. Instead, they're going to actually bind to this allosteric site over here. And when they bind, they change the shape. So it's no longer this nice flower shape. It's all kind of gone in on itself, and this is going to be what the enzyme looks like now. And now there's no active site available for the substrate to bind to. And so because it binded, it prevented the enzyme function because it's no longer having that active site. And so our reaction rate is going to decrease. So increasing substrate in this case cannot prevent the effects of a non-competitive inhibitor binding. We could have lots of substrate, but if all of them are inactive enzymes, then nothing is going to proceed. And like I said before, enzyme denaturization is reversible in some cases, but most times it is not. Sometimes it is. We are down to our key points for today. If you have any questions on these, you can let me know, but I have them written in here just in case you want to look over those key points again. Just a quick reminder that pH and temperature have an impact on how our enzyme is going to work. We're also going to see that the amount of substrate matters. The amount of enzymes are going to matter. We're also going to see that if there's competitive inhibitors or non-competitive inhibitors, all of those are going to impact what our enzymes can do or cannot do. That is it for our enzymes. Hopefully, this helps you a little bit with your lab, and hopefully, you're going to be able to figure out the answer of what your lab's supposed to do if everything works